In this lecture, we're going to talk about the binomial series again, and we're going to actually define what we mean by x to the alpha for alpha a real number. Okay, so recall the binomial series, 1 plus x to the alpha is equal to 1 plus alpha times x plus alpha times alpha minus 1 over 2 factorial times x squared, etc., etc. Let's define now what we mean by x to the alpha power. For any real number, define x to the alpha to be equal to the exponential of alpha times the natural log of x, whenever x is a positive number. Because natural log of x does not have a definition for anything but a positive number at this point in your mathematical career. Okay, so let's see now where this will take us. All right, let's do a basic theorem here. Let x be a positive real number, and for alpha and beta, any real numbers at all, x to the alpha times x to the beta is equal to x to the alpha times beta. We're going to prove that. And if f of x is equal to x to the alpha for some real number alpha, then the derivative of f prime is going to be alpha times x to the alpha minus 1. I mean, these are Calc 1 things. You've never probably really seen them proved to this point. The proof of 1, we just unroll the definition. X times alpha, x to the alpha times x to the beta. This is the exponential of alpha times natural log of x times the exponential of beta times natural log of x. We let exponential do its thing. We factor out the natural log in the argument, and then we go back to the definition, and we have it. Bang, there you go, the proof of part 1. To prove part 2, note that, okay, we take the derivative of f. Okay, that means we take the derivative of the exponential of alpha times the natural log of x. Okay, by the chain rule, it's equal to exponential of alpha times natural log of x times alpha over x. Alpha over x is just alpha times x to the negative 1 by a notational convention, and there we have it. In the last 2 lines we are done. All right, so let's now go back and actually prove the binomial series is what it is. That 1 plus x to the alpha is equal to the sum of k equals 0 to infinity of alpha choose k times x to the k. We'll prove it by induction. Let f of x equal 1 plus x to the alpha. We'll do a Taylor series expansion of f around the number 0. To do this, we will show that fk, that the kth derivative of f evaluated at 0 divided by k factorial is the same as alpha choose k. For this, it suffices to show that the kth derivative of f evaluated at 0 is equal to alpha times alpha minus 1, etc., all the way to times alpha minus k plus 1. Okay. Note that the first derivative of f at x is alpha times 1 plus x to the alpha minus 1 power. We get that from the chain rule. If we evaluate f prime of 0 at 0, that gives us a. Now suppose that for a fixed integer, our formula k, the kth derivative of f evaluated at x is equal to alpha, alpha minus 1, etc. times 1 plus x to the alpha minus k. We can then use that and take its derivative to get the k plus first derivative of f evaluated at x. Okay. And evaluate that at 0, and so there should be a plus 1 there in the exponent, but it gives us the formula that we should have, and so we're done. We have proved now the binomial theorem. Okay, given our proof of the binomial series, let's revisit our conjectures. Okay, we have 1 plus alpha x to the alpha power is the sum of k equals 0 to infinity, alpha choose k, x to the k power. And we have 1 plus x to the beta is equal to the sum of k equals 0 to infinity, beta choose k times x to the k power. If we take their Cauchy product, okay, this will yield the sum of n equals 0 to infinity of the sum of k equals 0 to n of a choose k, beta choose k minus n times x to the nth power. Okay, and so, and the power series representation of 1 plus x to the alpha plus beta is equal to the sum of n equals 0 to infinity of alpha plus beta choose n x to the nth power. We can then take these two infinite series and equate the coefficients of like powers and get that alpha plus beta to the nth power is equal to the sum of k equals 0 to n alpha choose k times beta choose n minus k, which is cool.